І зараз на сцену вийде людина, яка до нас приїхала аж з Варшави, з Варшавського університету. Це Карол Pieniący, і він експерт у сфері дронів, причому будь-яких, тих, які їздять, літають, повзають, плавають, роблять що завгодно. І зараз він нам про це все і розкаже. Зустрічайте.
Okay, can you hear me? Okay, great. Oh yeah, now you can hear me better. So yeah, first of all, this will be in English. And yeah, and I want to thank you, say my thanks to organizers for organizing this great event. And also I want to thank the Polish Academy of Sciences for this invitation. So today I want to tell you a bit about my journey and my experience with building autonomous systems, mainly for drones. But I want to tell you this on the examples of robotic competitions, and also how and why these competitions can apply to real world, and how can they help us develop some technology that will help us also in real world applications. So a few words about myself. I am a PhD candidate at the University of Warsaw. I also founded and led a team of programmers and engineers that's called Warsaw Motors. And I will later show you our competitions. So I am programming since I was, I think, 10. But at some point in my life, my programs started to be a bit boring because I coded something and it showed something on my computer or did something on the screen. But then someone showed me robotics, and robotics is a great way to connect our programming theoretical thing on some virtual machines with the real world, and it can once I seen how my code and what I create interacts with real world, then I was so hooked on this, and yeah, I never could go back to programming anything that just does something on my computer or my phone or whatever. And yeah, so this interaction with real world is, I think, my main point of focus, to create something that can work and interact in real world. And I want to say that this will not be very technical talk, so I don't want to get into details of how and why and what methods I use to develop those systems. I want to give you this overview and give you an insight of what the robotic competitions might give us, what challenges are presented, and how they translate to real-world applications. And this being said, I want to introduce only one small technical thing. So I want to define what is an autonomous system. So we say that some system, robotic system, is autonomous when it interacts and actually responds to its environment. So this is maybe easy to explain in contrast to automatic systems, when we just program some behavior and then the system, the robot or a drone, just follows the pre-programmed mission. So we need to have this element of maybe sensing or interacting with environment, with changing conditions, to talk about autonomy. And yeah, I want to tell you about this experience on 4 examples of my projects. So yeah, throughout the years, I had a few big projects that led to me actually working with autonomous systems. And in short, those are first is a competition that is directed to students and student teams to design and operate Martian-like rovers. It's done on Earth, but you'll see in a few seconds that it looks very, very, very cool. Then I did drone racing. So the idea here was to translate how humans do drone racing to eliminate human pilots in this loop and do this completely autonomously. Then it will be the only project that is not a competition. This is actually my master's thesis, and it's how to dock a drone with a robotic manipulator. And then lastly, I want to tell you a bit about my latest project, which was a huge robotic competition that actually took last 3 years of my life. Okay, so let's go first to this Martian rovers challenge. And first of all, what is the idea behind that competition? This competition is not, at least it was not, because I was taking part in those in 2017, was not oriented towards autonomous systems directly, but it was a very important step towards it. So this is a challenge that it takes place on Earth. Actually, there is a series of challenges, but the University Rover Challenge is the main one, the oldest one, and the most prestigious ones. So this challenge is actually about developing a Martian-like rover and operating it on Earth, competing in different tasks, both technical manipulation, also some automatic driving, but also very much science-oriented. So also with this Mars expeditions, we do a lot of science with our robots. So yeah, how does this look like? And this is actually a photo from MDRS, that stands for Mars Research Desert Station in Utah, in USA. But would you say this looks like Earth? I think this is a very great choice for environment and for the landscape to organize Mars competitions, Martian rover competitions at. So the environment very closely resembles that on Mars. And this competition is actually about building and operating a robot like this. This is our University of Warsaw's rover. And we do different tasks, different small challenges. Here, we are taking a toolbox. This scenario was to help an astronaut to deliver some tools to an astronaut. We can also have something like find an interesting rock. And this was basically it. The task was find an interesting rock. And as you can see, the interesting rock was the black rock with some red dots on it. And this would be great if we did it autonomously, but it was not required at the time. It was still 2017. And actually, the main focus of this competition was teleoperation. So we were preparing hardware, we were preparing cameras, we were preparing operator stations. But actually, almost everything was done manually by the operator. And this is an important step because it translates well. Actually, it builds a platform that can later be equipped with some automation. And it's a nice step towards these autonomous systems. OK, here is also a picture how we did operate a simulated panel, a simulated rocket panel with the rover. So in this scenario, actually, the operator of the rover is sitting, I think, about 1 kilometer from the side and is operating it remotely. So this very nicely verifies that we can use our sensors, cameras, and manipulator precision to operate this kind of panel from remotely, but still with the help of human operator. And later, these competitions develop into more autonomy and more autonomous systems. So my next project is the drone racing challenge. It's called Alpha Pilot. And it was organized by Lockheed Martin and the DRL company in USA. So they already organized the human pilot drone races, where human pilots race through a series of gates with very high-speed drones, very acrobatic FPV drones. And the idea was to basically build a new drone that's a bit bigger, and has enough computing power on board that we can replace human pilots with our autonomous software. So this was the idea. This was the purpose. This was in 2019. So it was still a bit early in our journey to automation, AI, and deploying machine learning on our drones and robots. But we tried, and the results were pretty nice. So this should be, I hope, is this a video? OK. I don't think it starts. Should I? OK, I should press it one more time. OK, we see a video. This is how we are flying through this short series of gates, right? And this was just a run from the simulator. And I wanted to show you that because that's how this problem was approached. So how to do this completely autonomously so that we place real drones on the starting line and just press start, and they race. So first, we did this in simulations, and this led to working with real drones later. I will speed up a little, so let's go next to the next slides and to the real drones. So this is a view from a real drone, and you can see that the gate is especially designed so that it's easier for the drone to recognize, for example, these checkers or some corners. And this should be also a video of how the gate is tracked and how the drone, in every possible second, knows exactly where is the gate that it's supposed to go through. And just to go to the later event, when it was developed on real drones, things did not look that well. So we have this problem that transferring solutions that are done in simulation to real world, to real drones, do not always go as planned. And this was still 2019, so we still did not have this much computing power. And this was not our drone. This was a different team that was running just before ours. This one is our drone. And actually, I'm very proud of the team, because we did manage, we were top 3 in the world to finish the whole track during this event. This was like the final event. You can see that the gate in the back was the final gate, and our drone was one of the first ones that made it all around to the end of the track. But yeah, this did not have a lot of implications to the real world yet, because it still was a bit difficult, and most of the teams struggled to go through first or the second gate. As you can see, there's a lot of drones that are crashed near the first gate. So yeah. Then going forward, this one is not a competition. This is not a competition organized by someone else. But I like to believe that when we have an idea and we say that, OK, this is a challenge for me, so then we define a challenge for ourselves, and it has, I think, as much power as any challenges that come from outside. So basically, this was completely my idea. I just wanted to do it. And I thought, OK, I have at my university this great robotic manipulator, right? So what I want to do, I think I want to try to catch a drone midair. And this was it. But basically, that's the whole definition of the challenge. That's the whole definition of the problem. And yeah, that's basically what I did for my master's thesis. So you can see the setup here. And the setup is like the drone. That's also an FPV-like drone. And a robotic manipulator. And actually, under the robotic manipulator, you can see a camera that is used to observe the drone. In this setup, both the drone and the manipulator are operated kind of autonomously, but yeah, this is a bit tricky because this is a very close to the line between automatic and autonomous operation. I would personally say that the drone was mostly automatic, but the robot was more adjusting to the environment and to what the drone is doing. But in the end, it was a collaborative effort of the drone agent and the manipulator agent to work together for a successful docking. And yeah, I think this should be a video. Yeah. So here we'll see how the operation is performed. So the drone, I mean, this is no human piloting at all at this point. So the drone is trying to hover in a position close to the manipulator that it will be possible for the manipulator to come and grab it. And the manipulator is adjusting and is actually sensitive to how, like where the drone is, but also how stable the drone is at that position. So here you can see a successful docking and turning off of the drone motors. I think I have another video with a different perspective. But during the video, I want to tell you, okay, but what are applications of this project? So this was also 2020, I think, so 4 years ago. I really was interested in autonomous drone operations in terms of real deployment in the real world. And for that, I think we definitely need reliable drone docking stations. So stations where drones sit, they can be charged there, maybe a payload can be changed, they can take off, and they can land there. So this was my idea, I wanted to test this approach to drone landing, where I don't actually land the drone, because the drone is caught mid-air, and then with the robotic manipulator, it can be very precisely placed in any space in a docking station, right? So this was the idea. But very soon after this project came the MBZ IRC. And this was my last endeavor on the robotic competitions topic. And yeah, it was a big one. So this was organized by Aspire in United Arab Emirates. This basically lasted for the last 3 years. This is a recurring event, but the last edition was actually made a bit more difficult, a bit more advanced. And to go through basically why, I will show you what was the idea for the competition. So the idea is like this. We have boats over some area of water. And as you can see, what the drone sees over this large body of water is basically a few pixels when a boat is pretty far, is a few pixels across per boat. But the first task of the competition is to find the boats on this area of water. So then, when we have found a boat, it may look like that. We need to identify that this boat is the one we are looking for. So 1 day before, we got a report that says, you are looking for that boat tomorrow. So, OK, we got that picture. If it matches, we are going through with it. And then what we need to do is, on the deck of that boat, there are some objects. There is a small object and a large object that we need to transport from the deck of this target vessel to our boat. So that's another element of the system that we not only have drones in that system that we are flying over water and picking up some objects, but also we have an autonomous catamaran like this one. That is actually the target for the objects, so we need to pick them up and place them here. OK, so as you can see, this combines drones and unmanned surface vessel into a whole system. And of course, the whole task was supposed to be completely autonomous. So literally what we could do is we could press start at the beginning. And we had 40 minutes for the whole task, and we need to patrol the area and do the intervention, go there with our boat near to the target vessel. So this is the idea for the competition. Oh, and there's one more thing. We were not allowed to use any external extra system navigation. So any GNSS navigation is out of the question. It was just not allowed. So we had to develop basically our own navigation that worked over water as well. So how did we approach that problem? First, we wanted a nice, solid fleet for our task. And yeah, I proudly present here our first drone. This is actually our scout drone. As you can see, it's a plane, but it has also the VTOL capabilities, so it can take off and land vertically in one place, but it's also an airplane that can be in the air for the whole duration of the mission. So the idea here was that the drone, or actually a couple of drones like this, were like scouting the area and looking for all of the vessel and maybe prioritize them which are the most likely to be our vessel. But then another drone, like this one, was sent to that target vessel, and we actually have a LiDAR here as well, so we can take a point cloud picture and we can match the vessel to the reference one and verify that this is what we are looking for. So then for the pickup, we have this small but powerful drone, and this may be interesting because the way we wanted to ensure that we will pick up this object is we have built a net under the drone, and the net was pulled back to one side, and the drone just landed on top of the object, and then the net was pulled under the object. So after that, we had this case in the net, and we could just take off, and we were sure that this will not fall out during the flight and transportation to our boat. Okay, need to hurry a bit. So this is what it looked like over water in Abu Dhabi. This is our USV. This is the verifier drone. We are doing a test run of our system. We actually had the capability of using our USV as both the target vessel and the destination vessel, basically. So when we didn't have any access to any other vessels, we used our USV as the target, and we were testing and iterating on the system. So this is what it looks like from the Scout drone. And as you can see, like in the beginning, I showed you that only a few pixels per boat are visible. And this is a real performance of our system. Like these are no labels, these are pure detections. So nowadays, this task is actually solved, so we know how to develop such systems that develop boats on the water. Then what we did is we did some maths on the geometry of the drone and the camera, and basically we could say that if the Scout drone sees a boat in this area of the picture, then this means that if we plot and calculate the line from the camera to the drone, we can actually know where it is, like in real-world coordinates. So then I want to show you what the verifier drone did when it arrived to the boat. And this will be a video in a second, but first I want to tell you what are we seeing here. So top left is the raw data from the LiDAR. Bottom left is actually separated and segmented into what is the reflection of water and what is the real points from the boat we are observing. And on the right, you will see a point cloud model that is built using this data while the drone is flying around the boat. So you will notice that at the very beginning, the right side will be empty because it just starts building. OK, let's watch it now. So yeah, that's basically what it looks like. It very quickly fills the right side with the points. And while the drone is flying around the vessel, we are building more and more detailed the model of the boat. And then we can actually match it to a reference model. So is this what we are looking for? OK, now going to the object pickup. We have this photo. It's actually from our testing in Poland. And yeah, we tried to develop our systems and our models like to be as resilient as we could. And it worked reasonably well on our data in Poland. But when we went to Abu Dhabi, we were so pleasantly surprised because it actually performed even better, or the best of all of our trials, because the weather conditions were just perfect. So the cameras could see everything there, and every case on the deck of the boat was always found. So yeah, that's basically it. This competition was very like multi-purpose, multi-module, and very like a lot of different technologies combined. But it allowed us to develop a lot of technology in this academic and like theoretical, maybe a bit area. And yeah, now we are in the process of going forward with this technology, with this IP, and doing something in real world with it. So if you want to find out more, we have a lot of more photos, pictures, and you can read more about the project. And the team that's doing last challenges is called Warsaw Motors. You can find us on socials. And yeah, I'm Karol Pieniący, and thank you. Are we doing Q&A? Okay, let's do some Q&A.
Yes, thank you. I see your hand, and thank you. Now I know the best task ever. Go and find interesting rock. I hope I'll have a job like that one day.
Thank you, Karol. Very, very exciting to see a fellow PhD robotics candidate. My name is Mitro. I'm a PhD robotics student. I'm just slightly a couple of years behind you, I guess, on a younger scale. I was very excited about the last projects you described with the UAVs under like boat tracking and like motion planning and everything. I have a couple of quick questions, maybe slightly technical, but not too much. So the first one, you mentioned LiDAR, and well, you had a couple of drones. You had a recon drone, you had a pickup drone. Was there any limit from the organizers, from the competition on the hardware, in terms of cost, or were you not limited? Like cost or like some restrictions?
Yeah, sure.
That's the first one.
The answer is no. This was the first competition that had almost no restrictions. So we were in charge of designing our fleet. We were in charge of choosing our drones. The only technical requirement was really that there is no no GPS receivers allowed on any part of any equipment at all. So that's the thing and it was checked a lot. And the second part was that we are supposed to be able to take off from 50 by 50 meters area on the beach. So the takeoff area was limited, but besides that, there was no limit. Also, there was no financial limit to the fleet. But I think that challenge was difficult enough. It sounded like an unsolved problem, how to pick up objects from a moving boat to another moving boat, that this was not a limiting factor. So what limited us was the challenge.
I see. Another quick one for the recon drone, for the Scout. What was the hardware, if you can share, the processor?
Yeah. I can tell. I mean, I also invite you and every one of you to later talk and ask me any questions you want. But don't want to get too technical here. But we actually considered at the point that we designed our fleet and our system and architecture, the Jetsons Orin were a bit new and not as stable as we liked. So we didn't use them. And actually, between Xavier's, so the previous series of Jetsons, and actually Intel i7 processors, we chose those ones. So we basically used mini computers that like Intel NUC with regular i7 processors. So yeah, I could talk a lot more about what are advantages of that. But basically, that was computers that have processors exactly like in your laptop.
I see. And the last quick one, you mentioned sim to real in your speech. And what about the last competition once again? Did you collect everything on your own, all the data? How did you bridge the gap?
So the semi-final of the last competition, was called the simulation phase. And the third phase, was the demonstration phase. So the broad idea was that the second the second phase is in simulator, and the third one is in real world. But we kind of knew, and from previous experience, that this does not really work. And what I can say is that we approached it more like two almost separate competitions. So slightly different ideas were used for the simulation, and then when we developed real fleet and real solution, there was slightly different approaches as well. And in the demonstration phase, of course, we used simulations for validating some of the subsystems, but we did not want to rely on the simulation almost at all, but as little as we had to. So we just did a ton of real-world testing, a ton of flying, and just testing with the drones.
Hello, Karol.
Okay.
Another question about the navigation, and the last competition was very interesting. How do you use the navigation without GNSS and without camera vision to find the objects?
Yeah. So this is a very interesting question, and I'm sure that's very needed solution, right? But I cannot tell you a lot of technical details yet, but yeah, this definitely was a challenging problem because the first approach to navigation is to use any visual clues. So if any external communication is not allowed, and the rules of the competition was that no external communication and no external navigation is allowed, so everything needs to be intra-system. So we need to somehow build into our system the navigation capabilities. So what we do have at our disposal is the starting gate, so the 50 by 50 meters area of land that I mentioned earlier. And we have our catamaran that can also drive on the water. So we had to use that. And yeah, what I can say is there were different approaches by different teams. So a lot of different teams tried to develop something, some radio navigation, some visual navigation with respect to the starting gate. What we did not want to do is to use any visual clues because we wanted our system to be more scalable, and anything visual will work only close to the shore, and we wanted it to be capable of operating on open waters as well. So we did not use any of the visual navigation for the large-scale navigation. What I can say is that our team was the only one to be able to fly drones out on the open water for the distance of a few kilometers. So this was quite a nice feeling there because, yeah, basically our drones were able and capable to go anywhere over the bay that we were flying on. What I can also say is that we joined this kind of navigation that worked everywhere with navigation using the LiDAR sensor. So once we switched to local frame of reference, so we were in more local environment of the target boat. So first of all, it was identified, but also we had a 3D model of it, so we could navigate with respect to that. And this LiDAR drone could coordinate everything that happened. So yeah, the local navigation on the scale of a few hundred meters max was done using the LiDAR sensor.
Okay, thank you. It's a great job. The last question. Do you know something about the curved graphene battery?
About the talk yesterday?
Yes.
Yeah, it sounds really cool. So what was the main takeaway for me is that it's not energy dense. And for my drones, I need energy density, unfortunately. But yeah, I think it can have many great applications in other areas. Yeah.
Yeah, thank you for the presentation. It was really cool. And my question actually about more planning and the control. And maybe I'm asking just for generic advice, not your particular solution. For your latest projects, maybe how do you think, is it worth to use a robotic operation system now? or it's over-engineered. Some people say that it's kind of over-engineered, but what is your opinion? Is it worth to use it nowadays for some? And what value it adds? Sensor fusion, maybe something like that?
Yeah. So, okay, this is like really, okay, two questions in one. So first is very specific about ROS, and the second one about general architecture. So about general architecture, I would say that we tried to do as much off-the-shelf solution as we could, because in such a complicated system, like we did not have capabilities to look into everything in detail. So we tried to take as many working black boxes as we could and just use them to build our system. And yeah, so creating the glue that will glue together everything is difficult enough. So that's what was our approach to like general architecture. And in terms of ROS, okay, this may be a bit a personal question about personal preference, right? So yeah, my personal opinion is that it is a great tool, and it can definitely help a lot for like maybe beginners, hobby projects, and intermediate programmers. But my opinion is that once you understand how the ROS is built and what it does really underneath, then you no longer need it. Yeah. So yeah. Basically, when you are able to do more specialized architecture for your solution, then you're probably better off without ROS and its overheads. And as I've said, this is a personal opinion.
Hi, Karol.
Yeah, hi.
Thank you very much for a fascinating presentation. So I would like to ask probably the most important question for today. How much explosives can it lift? Okay, I'm joking. Actually, the question about the drone racing. So how did you solve the routing problem? Because
Sorry, what
the routing problem, how do you navigate through the gates? Is this like a pre-programmed path, or do you use some sort of a computer vision to like process this real time?
Okay, so we did have the approximate layout of the track in beforehand. So approximate. So what we knew is that the track will look like this. So I don't know, it will be a C-shaped path, or there will be like an S that we need to turn and stuff like that. But during the runs and during the races, the gates could have been moved a little. And yeah, in the beginning, let's say that it can be like a few meters, maybe 2 meters or something, and they can be tilted about like, I don't know, 10, 20 degrees. But the general layout will look the same. So if the track looks like a C, it will still look like a C, but maybe instead of gates being like that, they will be shifted like that, and there will be a small correction needed. So in the end, the organizers did not do as much disturbance as they like promised to make it a bit easier, and it ended like you saw anyway. So the routing, your question was about routing. So we could pre-plan the path through the approximate track that we were given, and yeah, we used some mathematical models of flying the drone. Also, okay, fun fact, we also used some mathematics that's used to design highways that cars ride on. So this was a bit of mathematics there as well. Anyway, we used this planned route so that the drone knew what moves will be done, but there was a real-time correction in place. So if we actually appeared to be, I don't know, a meter or something off our track, our programmed track, so the drone thought that it should be there, then it was corrected, right? So that's basically how it solved the problem of flying the track. So this competition definitely had different assumptions. So a couple 100 meters, then I would look at search algorithms. It's no longer like racing and driving crazy fast, right? then it's more of like a calm drone that needs to do some search and not an optimized flight.
Hi, Karol. My
Yep.
name is Marichka. I don't have a science degree, but I have tried a drone simulator before. So I was curious, how would you compare a drone simulator to like the actual drone? Because like I get that simulator is more perfect than the actual drone. So, like, how much of real drone practice did you need to have to actually, like, to be confident that you know how to operate the drone?
Mm-hmm. So this is an interesting question also, and also a bit technical. Maybe it does not seem that way, because the way, like, how even I have flown as a pilot in a simulator, and how it does translate to the real world, also helped me and my team in designing the algorithms to do this autonomously. So there is this same gap that we have with autonomous systems, that we first try them on the simulators and optimize them for the simulators. And then to go to the real world, we have this gap that in real world, the situation is a bit more complicated. There might be more disturbances and more problems. And it actually is the same for a human pilot. So the experience of going and learning to fly on the simulator and then trying to fly real drone is very similar to the same gap when we develop autonomous systems in simulator and then fly them in real life. So the gap is definitely there, but it is like the same situation in autonomous software and with human pilots. The gap is there, but it's definitely better to first fly in the simulator because we are already much, much closer to the real world than not doing anything at all.
Thank you, Karol.
Yeah.
Давайте поаплодуємо ще.